Welcome to the Crazy Hat Chemist. So here's another video number 3 for determining rate laws and rate constants. So let's see if we can get started with this one. Let's see how fast our rate law is and our rate is for this reaction. Here we go. Bam! So we're going to derive the rate law and the rate constant for number 3. Okay, so we're going to derive the rate law and the constant. That's the K. So here's our equation here. We have H2SeO plus 6I plus 4H plus produces Se plus 2I plus 3H2O. Now again, it doesn't matter what the type of reaction is. It doesn't matter how many reactants, how many products. I don't care about the products. What I do care about is the reactants. So we're going to give a set of data for this one, and oh my, look at that. That's a huge amount of data. Okay, notice that this reaction is occurring at 26 degrees Celsius. So that means that any rate constant that we derive, we can use that rate constant at 26 degrees Celsius, but no other temperature without another equation. That's coming later on in this kinetics unit. So what we have here is we have 7 experiments. That's our first column on the left. Our next column on the left is H2SeO3. That is the change in concentration of one of the reactants. The next column is the hydrogen ion concentration. That is the third column. Those are concentrations of hydrogen ion. The next column is the change in concentration of the iodide ion. That's the next column. Then the final column on the right-hand side is the initial rate. And the initial rate is moles per liter seconds. All the other concentrations are moles per liter. Hopefully you see that. Now you notice that the stoichiometric coefficients do not matter on the balanced equation. Totally immaterial. What I do know is that the rate law looks something like this, and that is rate is equal to K times the concentration of the 3 reactants. There are only 3 reactants. They can be in any order. It doesn't matter. So I've changed the order from what you see there on the screen. But I am going to be solving for X, Y, and Z. I do know that X, Y, and Z are not necessarily the stoichiometric coefficients for the reaction. Therefore, I cannot put a 6 for the order with regards to iodine, and I cannot put a 4 with regards to the order for the hydrogen ion concentration. So that's something to note. So what we're going to do is we're going to find a set of reactions in which only one reactant changes but the others remain constant. So this requires an immense amount of analysis of this data. There are 7 experiments and there are 3 reactants. So that's a lot of information to compile and put together and unpack. So if you see in experiments 1 and 2, the hydrogen ion and the iodide ion concentrations, those do not change. So I'm going to be using experiments number 1 and 2 to derive the H2SeO3 order, and that is going to be X on that initial rate law that's set up there. So the H2SeO3 is doubling in concentration from reaction 1 to reaction 2. The initial rate is also doubling in concentration. So again, remember, if you double the concentration and the rate does not change, that's 0 order. If you double the concentration and you double the rate, that is first order, as in the case here. If you double the concentration and quadruple the rate, that is second order. Those are vast majority, the most common ones that you will receive is 0, first, and second order. Although there can be other orders as well. They can be negative, and they can be fractions, and they can be other values besides 1 and 2 and 0. So now what we're going to do is we understand that we just solve for X, that's equal to 1. So that's why we're going to place that in here like that. Then we're going to remove that, and then we're going to take a look at this data again and figure out, okay, what other 2 reactions have 2 of the reactants remaining constant? And again, this is a lot to unpack and a lot of data to look at. But you should see that experiments 1 and 4, both the H2SeO3 and the iodide ion concentrations remain constant. So now what we're going to be doing is solving for the value of Y, or the order of the hydrogen ion concentration. So between reactions 1 and 4, the hydrogen ion concentration is doubling. And then with reactions 1 and 4, the rate is going up by a factor of 4. So again, remember that if you double the concentration and you quadruple the rate, that means that this is second order, and that means that the order with respect to the hydrogen is 2. That's second order. All right. So now we've done the H2SeO3, we've done the hydrogen ion concentration, that's a H1+. Now we need to get the iodine ion concentrations order. So that's Z. Remove that information. Again, we're going to look at all this data and figure out which two reactions, the H2SeO3 and the H1+, remain constant, having the iodine ion concentration change and the rate change. And that happens to be experiments 1 and 6. If you see for experiments 1 and 6, the H2SeO3 remains constant, as well as the hydrogen ion concentration remains constant. The iodide ion concentration is doubling from reaction 1 to reaction 6. What happens to it from reaction 1 to 6? With the rate. So the rate is going up by a factor of 8. Now this is not something that I aforementioned. That is, if it is zero order, if you double the rate, if you double the concentration, then you do not change the rate. That is zero order. If you double the concentration and you double the rate, that is first order. If you double the concentration and you quadruple the rate, that is second order. So this is the next other possibility that comes up. If you double the concentration and then you triple the if you double the concentration and the rate goes up by a factor of 8, 2 to what power is equal to 8? Well, that is a 3. So hopefully you know that this is third order with respect to the iodide ion concentration. So now what we're going to do is we're going to pile all this information in there together to determine what the actual rate law is. So here's our rate law. Rate law is equal to R is equal to K times H2SeO3 to the power of 1, H1+ to the power of 2, iodide ion I1- to the power of 3. That's my rate law. So now what we're going to do is we're going to solve for the rate constant and the value of K. So what I've done is I've plugged in some information here from experiment number 7. So experiment number 7, the bottom experiment, I've used that information. I've plugged in the rate, 3.36 times 10 to the negative 7 moles per liter second is equal to K, the initial concentration at experiment number 7 for the H2SeO3, 1.0 times 10 to the negative 4 moles per liter to the power of 1. For the hydrogen ion concentration at experiment number 7 is 1.0 times 10 to the negative 2 moles per liter times the quantity squared, and the iodide ion concentration at 4.0 times 10 to the negative 2 moles per liter times the quantity, and that's cubed. So I'm going to rearrange all this, solve for the value of K, solve for the units of K, and here's what I get. 5.25 times 10 to the 5 liters to the power of 5 divided by moles to the power of 5 seconds. Oh my! That is enormous. A lot of information there. Okay, so I don't know if you found that easy or hard, but we're going to try this with an alternate method. And I find actually the alternate method actually much simpler because there's too much information to analyze on this one. There's too many experiments and too many things to find out, well, where are they being held constant? You really need a ruler to hold these two lines horizontally the same, and it takes sometimes forever to analyze that data. So let me show you the alternate method, and you'll find out that this one is actually easier. So here's our alternate method. We still have the same reaction. We still have the same concentrations that we did before. We know the basic rate law, and that is rate is equal to K times the 3 concentrations of the 3 reactants to the power of whatever those exponents are. So we're going to consider experiments number 1 and 2. Okay, so there's our rate law, our basic rate law. Rate is equal to K, H2SeO3 to the power of X, H to the power of Y, I to the power of Z. So we're solving for X, Y, and Z. Those are the orders with respect to the 3 reactants. So I'm going to take reactions 1 and 2. I'm going to take the 2 in the numerator, reaction 1 in the denominator, and I'm going to plug in the values here for this. Okay, and you should see that I have all the values here for reactions 2 in the numerator, reaction 1 in the denominator. And I'm going to solve for X, Y, and Z. The really nice thing about picking this one primarily as the first one is that you should see that with reactions 1 and 2, the hydrogen ion concentration and the iodide ion concentration are remaining constant for both of these. So I'm just actually solving for the order with respect to H2SeO3, which is X. Okay? So when I solve for this mathematically, I get 2 is equal to 2 to the power of X. What is that value of X? Well, that value is equal to 1. So now I know what this value here for X is. The order with respect to H2SeO3 is 1. And you can, again, what you need to do is validate this with what you got before and say, H2SeO3, I got an order of 1 for this. It's an order of 1 for this one as well. So this one was really simple. Now what we're going to do is use this information here, and this was the easiest one to get, where we're holding 2 of the reactants held constant, and we can solve for one of them. We could have used any of the experiments 1 through 7 to find where 2 of them are being held constant and then the other one isn't. So if you see that initially, you could solve for either the X, Y, or the Z first, and it really doesn't matter. Now what we're going to do, we have our same set of data, except for this time, we already know the results from the previous one, and that is the H2SeO3 is to the order of 1. So we're going to use that and looking at experiment number 3 and 4. Okay, so I know that the rate law is rate is equal to K H2SeO3 to the power of 1, so that's held there nicely. And now I need to look at just the H and the hydrogen ion and the iodide ion concentrations. So I'm ignoring the H2SeO3, unlike what I did in the non-alternate method. I'm going to look at the hydrogen ion and the iodide ion and figure out where those 2 are changing and where one of them is being held constant. That's all I need, is I just need to look at these 2 here and find out where one of them is being held constant. And it just so happens that with experiments 3 and 4, that is the case, because I already know the H2SeO3 is set at a power or order of 1. So I'm going to plug in the data here, and you should see that the iodide ion concentration with reactions 3 and 4, the iodide ion concentration is being held constant. The H2SeO3 is not being held constant. However, I know the order is 1. So it doesn't matter that it changes. What I am interested in is looking where the hydrogen ion concentration changes, and that's why I'm going to solve now for Y, because Z is being held constant, if you will, the iodide ion concentration. So I'm going to solve for this here mathematically. I'm going to get some numbers, and I'm again removing all the units for these. It's much easier if you remove the units, and we'll come back to that later on. So I'm going to rearrange this here, still solving. 4 is equal to 2 to the power of Y. So now this should be pretty simple here. Y is equal to what number? That is a 2. So now I know the order with respect to the hydrogen ion concentration. So this Y, the order with respect to hydrogen, is now 2. So hopefully that makes sense. Again, to recap on this, what we did is we knew the order with respect to H2SeO3, that's a 1. So now it doesn't matter that this changes with the experiments 1 through 7. We are looking for the hydrogen ion and the iodide ion, where one of them is being constant and the other one changes. And we don't really care about the rate, whether it is a nice, pretty number or not. Okay, now we're going to use this information here now that we know the order of the H2SeO3 and we know the order of the hydrogen ion concentration, and now we're going to solve for the next part. So we know the other two parts here, that is we know the order of the H2SeO3, that's 1. We know the order of the hydrogen ion concentration, that's 2. So our basic rate law looks like this. Now what we're going to do is we're going to find out where the iodide ion concentration changes. In fact, it doesn't matter which experiment we use now in these sets, because we have the H2SeO3, it doesn't matter what the numbers are because we know the order, and the hydrogen ion concentration, it doesn't matter what the numbers are because we know the order, and at this point in time, it doesn't matter which experiment sets we use because we already know the order for the, we're going to derive just the order for the iodide ion concentration. I happen to use experiments 3 and 7, so let's check that out. Excuse me. So I'm plugging in experiment 7 in the numerator, experiment 3 in the denominator. So you should see those values in there. Again, I'm removing all the units here, and we'll come back to that when we derive the value of K later on. So you should see here that the H2SeO3 changes from experiments 7 to 3. And that doesn't matter because I know the order. We also know that the hydrogen ion concentration changes, and that goes from 7 to 3, it changes, but it doesn't matter because I know the order. We do want the iodide ion concentration to change, and we do know that the rate changes. So we're good there. We're going to solve for what Z is equal to. So rearranging this, solving for some numbers, plugging in values, here's what I got. Okay, and then I am going to get 8 is equal to 2 to the power of Z. So now, again, this should be a really simple one for us. What number to the, so 2 to the power of what number is equal to 8? And that, of course, is a 3, just like it was in the previous one. But I find that this one is easier. So now I know the complete rate law for this problem, just like I did before, but I find that this is easier. It might take just slightly more time on the plugging in the numbers, but less time in analyzing the numerous number of experiments 1 through 7 that you have to analyze. So I think ultimately there's less time involved in this process, this alternate method, than the previous method where you really have to find out where 2 of them are being held constant all the time. This one you don't need to do that. So our rate law, which is the same as the rate law that we derived before, is R is equal to K H2SeO3 to the power of 1, that's the order of 1, H1 plus to the power of 2, that's the order of 2, and iodide ion concentration to the power of 3, which is the order of 3. So now that we have the complete rate law, now what we need to do is we need to solve for the rest of this. So, same set of data, now there's our rate law, and now what we're going to do is we know the rate law, now we're going to derive the value and units of K. We're first going to determine the value of K without the units, and we're going to use experiment number 7. Although any experiment will do. So, here we go. Let's keep on going. Don't slow down. You got this. Keep on going. Alright, so I'm using experiment number 7. Again, it doesn't matter which experiment you use. So I've plugged in the information from experiment number 7. I know the exponents. I know the orders. I'm going to plug that in. I have removed all the units to keep the math and the numeric values simple. Okay, and this is the value I get for my K, my rate constant. And my rate constant is 5.25 times 10 to the 5. Again, you should compare this to what we got previously on this same problem, but the non-alternate method, it's actually the same value. That's a check. Okay. By the way, if you're still enjoying this video, please give me a thumbs up on it, subscribe to my YouTube channel. Let's keep on going. Okay, now what we need to do, we got our data that we had before, we have our rate law that we had before, and now what we need to do is we need to derive the units for K, and then combine the K value and the K units together. Alright, so what I've done is I've used any experiment. It doesn't matter which experiment, they're all going to be the same. So I have now the units for k absent of the numeric value. I've rearranged this a bit so that k is on one side. We're going to cancel out some units. I've canceled out the moles, I've canceled out the liters. And remember, when you are multiplying exponents, that is L2 in the numerator times L3 in the numerator, you add up those exponents. So that's why I get the units of k are equal to liters to the 5th power divided by moles to the 5th power times seconds. So now what we're going to do is we're going to combine my numeric value of k with the units of k, combine those together, and with our rate law. So here we go. Combining this together and combining this together, we got one thing, and that is the numeric value of k and the units for k. So that is 5.25 times 10 to the 5 liters to the 5th divided by moles to the 5th times seconds. Don't go away. I have a few jokes here at the end, so don't go away. Hopefully you're okay with that. Hopefully that worked well for you. I really like this alternate method. I find it really simple. There's less data analysis to do with this method. Okay? Alright, so here's a little bit of elemental humor for you, and I thought that you were expecting me to wear that same hat that I did before on the 2 previous videos, and that was a root beer hat. But I decided not to do this. I'm wearing a different hat, and this is from something else, and this is from One Piece. Apparently, that's what it's from. So here's some humor for you. What does one do if one can't swim? Of course, you sink. Right? Yeah. Okay. What did the cowboy do with his horse? He rode him. Oh yeah. What did the gambler do with his cards? Palladium. Of course, these are all elements, and that's why it's elemental humor, but there's one more. Here we go. Sorry if those were really bad chemistry jokes, because the good ones are gone. I hope you enjoyed this video. I hope you enjoy my YouTube channel. Give me a thumbs up. Please subscribe to my YouTube channel. And I'm going to see you next time for more cool chemistry kinetics. And hopefully that rate reaction wasn't too slow for you. I hope you have a great morning, day, evening. I'll see you next time. Bye for now.